Ladies and gentlemen, hello, coming to you not quite live from One Take Studios, where my camera is already losing focus. Excellent. All right, guys, put on your seatbelts, get ready, take a deep breath. We are talking about an introduction to statistical tests today. All right, there's a lot of fine points here. The details really do matter. And so if you've got questions, by all means, ask questions. I realize that you can't talk to me in this moment, but find somebody to ask questions and pursue the answers, because understanding this is really going to be useful. We are looking at statistical tests today because kind of the whole point of statistics is to be able to draw inferences, all right, draw conclusions based on data that's been collected. All right, so we've done that previously by estimating values, and that's where confidence intervals come in. This is another alternative to that. Rather than using the data to come up with an interval that hopefully contains the mean, what if I had a mean and I just wanted to test it to see if it would stand true or not? Dangerous words there. All right, so here we go. Ladies and gentlemen, that is the whole point of statistical tests. We are going to try to make decisions concerning the value of a parameter. If you remember, a parameter is a number that represents a population. But we're going to be making these decisions based on statistics, which are from samples, of course. All right, we're going to start with something that's called a null hypothesis. This is our working hypothesis. This is what we believe the parameter to be, based on previous activities. A null hypothesis formally looks something a little bit like this. This is h sub 0. We have said that sub 0 in mathematical formulas indicates a starting point. So this is our starting hypothesis. And that hypothesis would be that our mean, again, notice population notation here, is a certain value. K is just a constant in this. K is going to be a number. So maybe we assume that from the start, the null hypothesis is that mu equals 75. There we go. That would be our number. All right. If this is what we are trying to test, well, then we need to have an alternate hypothesis to go with that. So we have our starting hypothesis, the working hypothesis, and then we're going to pose something that's alternate to that based on the sample data that we've seen. That could look like a number of things. Again, notice the notation. This is h sub 1. So this is the next hypothesis, different from our starting hypothesis. And that could be that perhaps I believe that mu isn't actually 75. K, whatever, but maybe I believe that mu is actually less than that. If it's less than, that's something we would call left-tailed. However, maybe the data is leading me to believe that instead of mu equals K, maybe I believe that mu is greater than K. That's going to be right-tailed. Or perhaps I'm led to believe that it's just not K. One way or the other, it's not K. It's not that value. It could be greater than, could be less than. That's what we call two-tailed. You are not choosing all of these. All right, so for what we're doing today, you have a starting hypothesis or null hypothesis, and you'll be selecting one of these. Please note the notation. Don't get sloppy, okay? All right. This is, world's smallest nutshell, I guess. We are saying that we are trying to compute the probability of a sample x bar compared to mu, compared to our original, and using that to decide whether or not we are going to reject our original value for mu. All right, so we're going to get together sample data, we're going to find an alternate mean, we're going to find out the probability of that mean, and use that to decide whether we're going to go with this or whether we have enough data to say, you know what, maybe I think it's something else instead. All right, again, deep breaths, we got this. The best way that I can think to do this is to walk you through an example beginning to end with all the fun details, okay? All right, this is my problem that I have created for you. Loretta's mean time to run 2 miles is 27 minutes, all right? So this is going to be what we are starting with. I did forget the end of that sentence. I do need to say also, so it's going to be a mean of 27 minutes with a standard deviation of 2.1 minutes. So notice that's going to be population, that's a parameter, that's a parameter. This is based on our population in theory. Her last 5 run times, however, are 26 minutes, 24, 25, 23, and 27 minutes. So we know that her mean time is 27. Maybe she's been doing this a while. Maybe, a lot of these values are actually less than 27. So perhaps this is outdated. Maybe her mean isn't 27 anymore. If I'm looking at this, maybe her mean is actually less than 27. So my question is, does the data indicate that Loretta's mean time has decreased? Maybe. This is what we're going to test. Use alpha equals 0.01. I'm going to explain this more as we go along. We don't need it quite yet, and I don't want to overload your brain. I want to try to get this to you in pieces. But this is what is called a level of significance. Alpha always represents a level of significance, and this is actually 1%. Common levels of significance are 1% and 5%. This will be given to you in a problem, although if you're creating your own problem, you can choose it. I chose to use 1% here. And we are going to assume the distribution is normal. Again, either you have to have that assumption in place, you have to know that that's a truth, or you have to have enough data values to be able to say, hey, this is going to behave normally. Again, having something that behaves normally allows us to make predictions that are valid. All right. This is only 5. Remember the magic number? Based on our central limit theorem, we typically would like to see samples of 30 or more before we make decisions. But if we know that this distribution is normal, we can use a sample size that is less than 30. Okay, here we go. You ready? Okay, I've given us a ton of workspace here, and we're going to see how this goes. I did put a reminder of this fun fact for you off to the side, just in case you want to take a look at it. And that is that z, so we're talking z-scores here, that's the number of standard deviations we are away from the mean, boom, is x bar minus mu divided by sigma over the square root of n. Alright, so we're going to kind of keep that in mind. We are going to start listing things that we know. So if we put everything together in one spot, and this is probably going to take more than this space actually, but we're going to start here. Things that I know. I know that my alpha value level of significance is 1%. So I'm going to put that someplace where I can see it. I also have enough information here to put together my null hypothesis. Again, note the notation. Hypothesis, my starting 0 hypothesis, is that mu is 27 minutes. Alright, so that's where I'm going to begin. That mu is 27 minutes based on previous stuff here. What will my alternate hypothesis be? Again, notation for alternate is h sub 1. And put my colon in there. Well, what do I suspect? Well, based on this question, I see the word decreased, and also then looking at these numbers here, I'm like, I think this could be less than 27. Less than 27. Which means that this is going to be left-tailed. And we're going to see a visual for what that means here shortly. Okay, can we use a normal distribution? Yes, because it says it's normal. Hence z. Z was our standard normal stuff, so this is going to make sense. So if I put this together, I'm saying, let's see. If I want to use this, if I want to find z, I'd have to know x bar. 26 plus 24 plus 25 plus 23 plus 27 divided by 5. Ladies and gentlemen, if you add that up, that's actually 125 divided by 5, which is 25. Alright, so these 5 values actually have an x bar of 25. So we're saying the population is 27 minutes, but this sample has a mean of 25 minutes. So we're going to compare these two to see what happens. So we are looking at here, z is equal to, we've got 25 minus 27, and dividing that by, we do know that sigma was 2.1, so 2.1 over the square root of, what was our sample size? That was 5 right there. Okay, so we've got all of those values right there. Which, by the way, in case you don't trust me, you can calculate yourself. This has a value of negative 2. I'm going to call it 13. All right, that does keep going. I did a round. So negative 2.13. Okay, I really, really, really want you to have a visual of what's going on here. This is a sketch. It is hopefully a halfway decent sketch, but it is a sketch nonetheless. There we go. There we go. What are we saying? We are saying that this is centered. Well, if we're talking standard deviation, it's centered at 0, but that's really representing 27. We're saying that 27 is the mean, and all of this data is going to be distributed normally around 27. Well, so where is 25? 25 is not at 27. Again, please keep in mind this is a sketch. Boom and boom. So this would be 25 here. So we're looking at where is the 25 compared to the 27. Well, what is this? We just said that this has a value, a z-score of negative 2.13. In other words, this is my raw data values here. Alright, so the 25, 27, those are raw data values. Can you see that in pink okay? Yeah, you can. If we standardize this, if we say that 0 is the center, then 25 is 2.13 standard deviations below the mean. So raw data, 27 is at the center, 25 is based on our sample. That's our mean here for these 5 numbers. But 0 for standardization would be the center, and then that 25 is actually a little bit more than 2 standard deviations below the mean. Okay, so what does this mean? Well, we talked about, for our nutshell, the probability of this. So the probability of this would come from what's happening right here. What is the probability that we have a value all the way down here? Isn't that pretty? Pretty in pink. There we go. Well, how do we find that value? We do have a z-score. We could look it up on table 3, I think it was in the back of the book someplace. So we could look this up on a table. We could do some stuff with normal CDF. We could do that. That's a possibility as well. But ultimately, I would really like to know what this area is. Remember, this area is also a probability. I would like to know what this probability is for this space right here that's shaded. When I compare the 25 to the 27, what's the probability that I'm going to end up here? And there's a few ways that we can do that. I am going to, at this point in time, jump over to the calculator. And I do want you to see something, by the way, in case you didn't believe me earlier. That's what we've got there. Boom and go. So that was calculating that z-score of negative 2.13 is what I called it. There's our calculations with that. I'm going to go to my menu where everything fun and excited is located. And since we are still working in the world of statistics, I probably want to go there. Oh, new menu item. Do you see it? What's at the bottom of that? Stat tests. We're trying to test stuff, right? I bet you there's something good there. Let's go to stat tests. And because we're talking about z-scores and because we know it's normally distributed, let's go with that first option there. Let's go with a z-test. That seemed logical. What do we have? Do we have data or statistics? Technically, we have both here. All right? If I was running this out of a spreadsheet, I would probably go with data. Since I happen to know my z-score right now, I'm going to go with stats instead. All right, I have some statistics that I can use. Okay, great. Think about how this compares to what we've already talked about. We have, this is the initial value for mu. This is your null hypothesis right here, which we said was 27. We said that we knew that the standard deviation was 2.1 minutes. So that's a comma. Oops, 2.1. There we go. And we said we knew that x bar was 25 because we added up our 5 sample values and divided by 5. And there were 5 values, so there we go. Which alternate hypothesis are we going for here? Again, we need to choose one. And our suspicion, oh, by the way, notice ha? That is the alternate way for writing h sub 1. It is the alternate hypothesis. So some people, instead of writing h sub 1, will write h sub a. That's fine. You can do it either way, whatever you prefer. But we are supposing that we believe that the value is actually something smaller than the null, less than, so we're going to go here and click OK and get this whole bunch of crud. What the heck is going on? All right, well, notice a couple things here. Most of this we already know. We know 2.1 is our standard deviation. We know we have 5 in our sample. We know the x bar is 25, and we actually already found our own z-score. Did we have to do that? No, but I wanted you to see that number so that we could graph it and make some sort of sense out of that sketch there. This right here, this is what's important. P-value. What does P stand for? Probability. Yeah, okay. So I'm going to take a moment to label my picture here, and I'll come back to it in a second so you can see it. But that P-value is, let's see, 0.0166. That is known as the P-value. Okay, P-value. So jumping screens again, right? There's my other screen. There we go. All right, so this has a probability, an area, a p-value of 0.0166. I'm going to kind of put that again in pink so we can pop it off the page a little bit better so we can read it. That is that space right there. So what we are saying is that the probability of getting 25 or lower as an x-bar, assuming 27 really truly is the mean, is not super likely. It could happen though, all right? We're talking this is going to be a little bit more than 1%. So this would be 1.66%. How do we decide? How do we decide if this is something significant enough for us to change our minds? How do we decide if this is something worth abandoning the 27 minutes in favor of something that is decreased, something that is smaller? Okay, are you listening to me? Are you listening to me? You want to compare the p-value to, let's see, compare, I'm going to write it out. Compare the p-value to your level of significance. All right, I told you that I would come back to that. Okay, this right here, this is how you make your decision. That's really hideous, but there you go. Compare the p-value to the level of significance, and that's what's going to determine if we're going to go with the original hypothesis or abandon it in favor of something else. Now, okay, I'm giving us some space to write here. All right, what am I going to do with this? Okay. We know where the 27 is compared to the 25. We know that this is a little bit more than 2 standard deviations away. We know that it could happen. The probability of that is a little bit over 1%. And we know that our level of significance, the alpha, is 1%. Are you listening to the words coming out of my mouth? What we are looking for in a p-value is something that is so unlikely that we have to say, you know what, this couldn't happen accidentally. Not really. Because the probability of it happening is so tiny, it's ridiculous. Therefore, if this is ridiculously small, I'm going to abandon my null hypothesis in favor of the alternate. If this is ridiculously small, that's significant to us. Notice the use of the word significant. If this is really small, this is significant enough to abandon this, because this is saying what's the probability of 27 actually being the mean and this happening anyways? I know that you don't get it yet. Keep holding on there, all right? Keep working with that. All right, now, here's what I'm going to say. I am comparing my p-value, which I have found is the 0.0166, and I'm comparing that to my level of significance, which was the 1%. This is a little bit more than 1%. This is 1%. This one is bigger. Is this ridiculously small? Is this such a freak show that we would abandon the original hypothesis? If it is bigger than your level of significance, it is not significant. Because this is larger than 1%. We are saying, this could happen. Yeah, it's small, but it's not like super small. I'm going to stick with the 27. I'm going to stick with my null hypothesis. So if your p-value is larger than your level of significance, you're going to stick with the null hypothesis. Consequently, that would mean if your p-value is actually smaller than your level of significance, you would abandon the 27 minutes and you would say, hey, there's enough data here that's significant that the time has decreased. I'm going to tell you, practice, practice, practice is the only way this is going to start to get even remotely comfortable to you. Please write down whatever it is that you need to write down to try to make this make sense for your brain. But let me pull this together in a statement. All right. I'm going to say this. The data is not significant enough. Pausing right there. What makes it significant? An extremely tiny p-value. This is not considered to be an extremely tiny p-value. It would have to be less than 1% to be considered extremely tiny. Tiny is significant. Therefore this, because this is bigger than 1%, is not significant. So this is not significant enough to reject putting in context, Loretta's mean run time of 27 minutes. Okay. This statement tells me whether or not my data is significant and the decision that I've made. It is not significant, therefore we have not rejected the null. In other words, we are saying we're going to stick with the 27 minutes because there's not enough here to convince us to go away from the 27 minutes. Your wording here is everything, and I cannot tell you how many people mess this stuff up. Your statement needs to say something to the effect of whether or not it's significant, and either it is significant enough to reject, or it is not significant enough to reject. And right now it's not significant enough to reject. We're going to stick with the 27. Watch your wording with this, because notice my word reject. You want to stick to that word and actually try to avoid the word accept as much as possible. What we are saying here is that I don't want to accept this, but I don't have enough data to reject it. This statistical test process never proves anything. All right, we don't prove anything conclusively. We just say, hey, we've got enough data to reject this, or we don't. And notice, what am I rejecting or not rejecting? The null. Please do not reject or not reject the alternate. All right, the alternate is simply used to determine left tail. It's used to get us our probability. All right, but keep your rejection or lack of rejection statement tied to the null. Okay, so don't tell me right now that we are going to be rejecting the fact that it's decreased. All right, there's a whole lot of danger involved with that. Just stick to either I'm going to reject the null or I'm not going to reject it. I don't even use the word accept. Okay, is this weird? Yes. Will it get better with practice? Yes. Do I suggest sticking to this format? You better believe it. Okay, but this actually has all the pieces that we would need here. All right, so it's all tied together. We've got everything that we use for data. We found it using the calculator, value, p-value, comparing it to there we go. For those of you whose brains can handle this right about now, guys, what if I had used a 5% level of significance? If I had used a 5% level of significance, would 1.66% be greater than 5%? Heck no. At the 5% level, we actually would have rejected this. So it all depends on this comparison between these two right here. So because I can change the level of significance to 1% or 5% or quite frankly whatever I want, it's just fascinating, and this is just a brief overview, with this being the level of significance is actually the probability of you making what's called a type 1 error. Type 1 error is the threat of rejecting the null when it's actually true. All right, so this is the probability that I'm willing to accept that I might accidentally reject the null hypothesis if it's actually true. If I make this bigger, if I increase this, I can lessen that probability. However, if I lessen that probability, I actually increase the probability of making a type 2 error, which is accepting the null when it's actually false. So this is a really fine line to walk on. You can't take one type of error and lessen its likelihood without increasing the likelihood of making a different error. So either we might accidentally, based on the data, sort of kind of reject something that's true, or we might accept something that's false. And we don't really want either one of those things to happen. So there's a whole line of very carefulness that we need to walk with this. Okay? All right, so practice it, take a look at it, try to make sense out of it. All right, please try to make sense out of it. If all you do is just say, tell me the steps and I'll do them, your brain will never get this. All right? Thanks. Have fun.